Hello? Okay, yeah, it works. Oh, sorry. Here, I'll take it. Okay, is that it? All right. Reminder that Friday is the drop date for all your classes if you're taking the 16-week courses. So you have until Friday to drop if you want to. Okay, just passing on the information. You have a mini exam that's due on Wednesday, and I just want to kind of briefly explain one thing on that mini exam. On the second problem, the one on the back, that problem has to do with change of variables, and the setup is the hardest part. The integral is going to be real clean and easy. All right. I redid all the lecture videos from last Wednesday because I wasn't happy with the way they came out, and I think I did a better job explaining it. And maybe I'm just being picky, but I did 2 examples in that video, and then along with that, the homework videos have a few examples. So that should help you with that second problem. But I'm going to move on. Chapter 13. On your desk, you will find a 8-page formula summary. Okay. These are all the formulas that we're going to be using in Chapter 13. And so I figured I would just give you a copy of them and just keep this as a reference. I may or may not allow this on the final. I don't know yet. I have allowed it in the past because it's a lot of formulas to remember, right? All right, let's go ahead and get started. Chapter 13. We are in the vector calculus section of the course. So we're going to get back to vectors. I don't know if you noticed, we kind of stepped away when we were doing double and triple integrals. You know, we didn't really deal with vectors, right? So now we're going to bring those back in. So 13.1 is called vector fields. This is going to be a very short section. First of all, what is the definition of a vector field? In 2-dimensional space, it says let D be a set in the plane. A vector field on D is a vector function capital F, notice the vector notation, that little half arrow, that assigns to each point xy in the domain D a 2-dimensional vector f of xy. So one of the classic examples is a magnetic field on a flat sheet of paper. So if you put 2 magnets down, North Pole, South Pole, and you put some metal filings around it, the metal filings will kind of move themselves into the direction of the field. Have y'all seen that before? Okay. So if I look at this as being like the x-axis and the y-axis, then if I pick some arbitrary point in the plane, right, so this is D, if I pick some point x, y, there's some direction which those filings are kind of lining up in, and there's a strength of the field at that point also. And so the way I tried to do this, and I just kind of guessed here, is that it looks like if you were at that point, you'd be pointing in this direction, and this length of this vector is kind of like the strength of the field. So if you're here, you have a longer vector, which means the magnetic field is stronger here, and the direction is different than up here, right? So every point in the actual domain, there is a vector at each point, right? That's a vector field. Another example of this is if we look at like a hill, right? Here's a hill and here's another hill. That's in 3-dimensional space. We look at it from the top, we get the topographical map of this, then we draw these, what we call level curves, so these are like the elevation lines. These lines looking from the top correspond to the elevation lines here, right? And what we can imagine is going to some point, okay, it doesn't matter where it is, and at that point, putting a ball there and seeing which way the ball goes, right? It would start rolling, and it would roll in some direction. So at that point, you would have a direction, and then depending on how steep the hill was, how fast it would want to go in that direction. We could represent that as a vector. Understand? And I found these online, these pictures. This is a picture of a topographical map where they actually put all those little vectors in. So you can see, like, if you're at different points, where you'd be where you'd be rolling to. And I don't know, yeah, it looks like there's different lengths to these, right? This would be a vector field. Understand? At every point, there is a vector. That's different than a vector curve, a function that we drew earlier, a vector function, r of t. Remember this, r of t equals, and then we had like either a two components or three components, and this would draw a curve. Remember that? Okay, this would be a curve. This is a vector function. It only defines vectors at certain points. This vector field defines, you have vectors defined at every point in the domain. So here's another example. And this time I actually told you what the vector field was. So we were given the vector field is defined to be the vector negative y comma x. So what I wanted to do is just kind of real quickly draw out a couple of the vectors. So let's just pick a point. What is the vector at the origin? The 0 vector, right? So when I'm at the origin, which you can kind of see with this black dot, I'm the 0 vector. Now let's go somewhere in this space. How about we go to 1, 1. So I'm going to move out to the right 1, up 1, to that point. What vector is there? So what? Negative y, which would be negative 1, and then 1. So that would be a vector. From that point, I go to the what? How do I do this? Go left 1, down 1 from this point. Left 1, up 1, sorry, thank you. Left 1, up 1 would be here, so I'd have a vector like this. Understand? Now what if I move up a little bit? Let me go to F1, 2. So now I'm right here. Let's see how the vector would change. What would it be? Negative 2, 1. So I'm going to move left 2, up 1. So this time I go left 2, which would put me 1, 2, and up 1, which would put me here. So the vector should be longer, right? Understand? And I could do this for all the points. And if I did it for all the points, then, well, let me move this point around first. Let me see if we got it right. Let's see, I move there. Okay, see that? 1, 1. If I move up a little more, 1, 2. I missed a little bit. All right. Now I'm actually going to show you, this is a lot of them drawn. Okay, having the computer draw a lot of them for me. And so you kind of get this feel that there's almost like this circular rotation, right? Doesn't it kind of feel like that's what's happening here? Got this rotation going on. And as you move away, what's happening? As you move out away from the origin, they get longer, right? So if this were like some sort of magnetic field or something, it's kind of a weird one, but at 0 you would have nothing, and then as you move away, you've got this field that's getting stronger as you move out. Make sense? Okay. I don't think I'm going to do any homework videos for this section. The first few problems are draw some vector fields. Okay, I don't think that's really worth me doing a video for. Like this one, here's a different one. You can type in anything here. So if you've got this downloaded on the computer, you can actually create your own vector fields and have it graph it for you. Okay, so what about if we look at a vector field in R3? So now you're in three-dimensional space. So you now have some region E, all right, in three-dimensional space. And you're going to define at every point in that three-dimensional space a vector. So that would be capital F of x, y, z. You give me where you are, I'll tell you what the vector is. This is a picture of, it's a computer rendition of the Earth's magnetic field. I found this online too, all right? I thought it was a pretty cool picture. You can kind of see, you know, it's supposed to come around and come back in like this. And towards the center here, towards the surface, away from the poles, it's just kind of messy looking, right? So at every point, we have some vector that represents that magnetic field. Now, drawing a vector field in three-dimensional space is pretty difficult to do, right? When you think about it, we've been trying to draw things in 3D, right? And it's been hard enough. But imagine trying to draw a vector at every point in 3D and then trying to make sense out of them. So check this one out. I'm just going to move this point around first. So at every point, there is a vector. Do you see my point moving around? Okay, so at every point, you see the vectors changing? Now, if I show you all of them, I don't know. Can you make sense out of that? And then if I get like a bunch of them, it just starts to look like a big, you know, cluster of arrows. You can kind of still see some weird wavy action going in here. Could you all see that? You can have the computer do something a little less dramatic, something like that. But still, you have to kind of move it around to kind of see what's going on. Right? Okay, here's an example of a vector field, a pretty famous one. So let me show it to you. Where are they all headed? They all look like they're headed towards the center, right? Towards the origin, 0, 0, 0. This is a good example of a gravitational field. Right? So at every point, you have this center-seeking, right? Center-seeking thing drawing you in. The problem is that the Earth's not round, so the field doesn't act exactly like this. But we can get pretty good models that do good enough for what we need to do. Okay, you have the basic idea of a vector field in 2- and 3-dimensional space? Okay. Someone has to give you the field, though, right? And someone has to tell you what the field is for you to start to do any work. All right, remember back earlier in when we were first learning about partial derivatives, we defined this thing called the gradient. So what we did is we took a function, in this case a function of two variables, f of x, y. We call this a scalar function because there's no vectors involved, right? If I graph a scalar function, what does it usually draw? A surface, right? In three-dimensional space. So if I take this surface, right, and I ask you for its gradient, you're going to create a vector which is going to be the partial derivative of this with respect to x. That's the first component. Second component is the partial with respect to y. And we'd use this little notation right here, right? If I have a three-dimensional or a scalar function with three variables in it, right, then I can also ask for the gradient, which you would do the same, and you would get a vector with three components. So in either case, if somebody gives you a scalar function, you can always create this vector from it, right? We call that vector, we call it the gradient vector, we call it the gradient vector field. Because you're creating a vector field, right? It's a vector. This is a vector function, isn't it? And this is a vector function. So it comes from the gradient. We call it the gradient vector field. Now it's going to have some important, you know, implications of that vector field later. So here is a function of two variables graphed right there. Do you remember what the gradient was? Geometrically? That's right. If you point in the direction, if you're standing on a surface and you point in the direction of the gradient, you will be pointed in the direction of maximum increase, right? Maximum ascent. And if you go and you just multiply by -1, you'd be pointing opposite, so you'd be pointing in the direction of the maximum descent, right? So here we have this surface, and I'm going to calculate its gradient. And then I'm going to plot its gradient, the gradient vector field. So here is the gradient vector field. okay, that should be, I guess, good enough. Can you see the gradient vector field laid on top of this? So this surface, we're looking at it from the top. This gradient vector field shows me all the directions, like if I'm at this point, I should go in that direction for the steepest descent. If I'm at this point, I should go in that direction for the steepest descent. And that corresponds over here on the picture. Let me try and move this around. I'm going to move it right there. Okay, so you see the point right here? It's saying go in that direction for steepest descent. And I hope you can see that. We're right here. If I go in this direction, right, go in that direction, I'm going to go up that lip. You see it? Okay, so the gradient vector field for this scalar function actually tells us what would happen if this were a ball on the surface, right? Now, if I let this ball go, it's actually not going to go up, right? Gravity is going to, but it'll go in the opposite direction of that gradient. Understand? So there is a very nice connection between a surface and its gradient vector field. All right, a definition. Now, please pay attention to the wording here, because from now on, if you hear me say, oh yeah, but that was, that's a conservative vector field, you've got to understand what that means. So a vector field, capital F, is called a conservative vector field if there exists some scalar function little f such that capital F is the gradient of little f. What? All this means is that the vector function we're looking at is the gradient of some scalar function. So let me try and give you a quick example right here. I'm gonna just give you this. What is this right here? What type of function is that? Vector function? Scalar function? This is a scalar function, okay? I would like for you to tell me what the gradient vector field of this is. So what's the gradient vector field? It's the vector we form by taking partials, right? So 2xy, that's the partial with respect to x. Partial with respect to y, x squared, okay? This is, I could define this to be my capital F, right? So this is a vector field that comes from the gradient of a scalar function. Therefore, this is a conservative vector field because it comes from the gradient of a scalar function. So here's our challenge. This is one of the main things we're going to get to later, is let's say that I did not give you this, and all I gave you was this. And my question to you is this a conservative vector field, yes or no? Well, what would you have to do to determine whether or not this was a conservative vector field? What's that? Yeah, you'd have to somehow go backwards up to f, right? And tell me what that f, well, what that function of two variables is, right? And it turns out that not every vector field comes from a scalar function. Not every one of them does. There are only a certain category of vector fields that actually come from the scalar, from the gradient of a scalar function. So they have a special name. They're called conservative vector fields. You with me? Okay. We will do this later. We will go and start here, and we're going to do partial integration is what we're going to do to get back to this. And it'll be kind of weird, but it's kind of fun. And then later on, we'll get a theorem. And a theorem will allow us to check whether or not a vector field is conservative very easily without doing all this hard work. But we got to work up to that, all right? Okay, y'all still on board? Yep. Yes? Okay. That's it. So look, let me just explain what this homework is. The first few problems